In many data domains, neural architectures are constructed with a specific understanding of the domain at hand. In many cases, the architecture constructed with a domain-specific understanding is often able to perform much better than using a conventional architecture on any type of input. Sequences and images represent two such types of data. In this video, we will discuss the processing of sequence data. Sequences might correspond to time series, sentences, or biological sequences. Sequences have some special properties which make them hard to process for neural networks. First, the successive elements of a sequence are not independent of one another. Therefore, using a neural network that is not aware of these types of sequential dependencies is an inefficient way to construct the architecture. Second, the length of a sequence can be variable. So, for example, the length of a sentence may vary. In such a case, it again becomes a challenge how to use a conventional architecture which has a fixed number of inputs. In this video, we will discuss recurrent neural networks which are specifically designed to handle sequence data. So why is it challenging to process sequences? Conventional neural networks have a fixed number of input dimensions and a fixed number of outputs. Furthermore, no prior information about the relationships among the input dimensions is built into a conventional neural network. On the other hand, sequence data often has variable length in which the different dimensions of the sequence, that is the different elements of the sequence, are closely related to one another. So for example, let's look at the case of text data. So if you pick out any particular sentence of text, the length of the sentence may vary. Furthermore, the successive words are not randomly related to one another, but they depend on one another depending on the specific properties of the language at hand. Similarly, in a time series, the successive elements of the time series are closely related to one another. Furthermore, the length of a time series may be variable. Similarly, in biological sequences, you have sequences of, for example, amino acids, and again the length can be variable. So recurrent neural networks can address such domains by building an architecture which is aware of these specific properties of sequences. So let us now look at why it is so hard to use a conventional architecture in order to process sequences. So in order to understand this point, let's look at a specific case of sentiment analysis. Now, it is possible to create a conventional architecture for sentiment analysis of individual sentences. What you can do is that each input might correspond to a specific position in the sentence. So x1 might correspond to the first word, x2 might correspond to the second word, and the inputs might be one-hot encoded. So here you note that I have denoted a rectangle for the inputs because it's a vector-centric architecture. So the circles correspond to scalars and the rectangles correspond to vectors. So the input is a one-hot encoded vector telling which word in the lexicon is the first set of dimensions, then you have the second set of dimensions, and so on. And the output, of course, is a sentiment. So we are looking at so here the sentence analytics is hardly any fun. So presumably it's a negative sentiment. So let's say it's a binary classification problem where you're trying to find positive and negative sentiments. Now, the first thing you'll notice is that you have already created a fixed architecture upfront with 5 inputs. So how are you going to handle sentences with length larger than 5? The second point that you will notice is that even though in this architecture we are always ensuring that the input for x1 corresponds to the word before the input for x2, the architecture does not have prior knowledge of this fact. What this means is that the architecture will also have to learn this fact in a data-driven manner. Now, one might say, well, if I have sequences of limited length, then maybe I can have that maximum length as the possible number of inputs. But even then you have a problem. So what do you do if you have sentences smaller than that length? So if you have a sentence smaller than that length, you will have to deal with missing inputs. So The other point is that what you really want to do is that you want to have an architecture which has a variable number of inputs but a fixed number of parameters. Now note that we want to look not just at sequences of limited length such as sentences. We are talking about sequences like, for example, weblogs, which might have thousands of elements or even hundreds of thousands of elements. So how do you process that kind of sequence? Because then you would have to, it would just blow up on you, the number of inputs. And then the second point is that in many of these sequence-centric applications, even your outputs are not necessarily labeled. So here we looked at sentiment analysis. So your output might also be a sequence. So for example, if you're looking at machine translation, the input might be a sentence in English and the output might be a sentence in Spanish. So again, you have a variable number of outputs as well. So recurrent neural networks can handle all these types of complexities. So what are the desiderata for architectures processing sequences? First is that the architecture should have some kind of awareness that the successive elements of the sequence are dependent on one another in some way. So you don't want to have an architecture which has to learn that from scratch, where you're not telling the architecture that, hey, element x2 follows just after element x1. And the way recurrent neural networks does it is that the ith element, it ensures that the ith element in the sequence, it is fed into the neural network after the network has had a chance to see what came before it. And the way you do it, where you enforce is that you feed the ith element of sequence into layer I. Now note that in all the conventional neural networks that we have seen so far, the input is always the first layer. Here, what you're doing is that you're allowing the feeding of successive elements into upstream layers. So as layer by layer, so the ith element is feeding into layer I. So what the ith element sees is everything, all the sentence before it, the hidden state that has been processed based on the portion of the sequence before it. So here each layer is associated with a timestamp. So what you have is what is called a time layered network. So obviously, since the length of your sequence varies, you will have a variable number of layers. So what have you really done? What you have really done is that each layer still has a fixed number of inputs, but because you have a variable number of layers, you can have a variable number of inputs. Now, this idea of putting the variable number of inputs by allowing a variable number of layers, the beauty of it is that such a network can be trained using backpropagation. Now, the second point is that obviously if the number of layers are increasing with the size of input, the question arises that how are you going to ensure that you have a fixed number of parameters, because each layer is going to have its own set of parameters. Well, the way it's enforced is by using shared weights across layers. Now, what the shared weights across layers ensures is that any element of the sequence can be approximately predicted by using a fixed model of all of its preceding elements. So what you have is that the number of weight parameters becomes independent of the number of layers. So let's look at a pictorial representation of these desiderata. So here I have shown an example of a recurrent neural network. So let's first focus on the image on the left, because the one on the right has a loop and often that tends to confuse people. So let's first look at this. So here you have a time layered network where you have a simple sentence, the cat chased the mouse. And what you want to do is that you have a language modeling application. So you want to forecast what the next word will be based on the portion of the sentence that you have seen so far. So here you have a variable number of inputs and a variable number of outputs depending on the length of the sentence. So here what happens is, now here I have not shown that typically you'll also have some inputs for the start token and the end token. I have omitted them here, but we'll discuss that a little bit later. So here what happens that you have an input state x1 which corresponds to the one hot encoding of the first word, and the input and similarly x2 corresponds to the one hot encoding of the second word, and then you have that feeds into a hidden state. So the x1 feeds into the first hidden state, And optionally it can produce an output, if you want to, for example, that depends on the kind of application here. So for example, if you're trying to predict the next word, which in this case is cat, that will be the target word. So y1 again will be a vector of probabilities. So it's going to tell you for each word what is the probability. So the loss function, again, note that they are being computed along all of these outputs, like in any other neural network. Now, the other very interesting point, now this is a vector-centric architecture where I've used rectangles because each of these nodes, it's a vector. And the other point that you'll note is that the weight vectors. So WXH represents a weight matrix between the input and the hidden layer. WHH represents the weight matrix between two hidden layers, and WHY represents the weight matrix between the hidden layer and the output. Now, the point is that these weight matrices, they are shared across layers. Every layer uses exactly the same set of parameters. So the intuition here is that at every layer, what you are doing is that you're computing the same function based on everything you have seen before it, as well as the next input. So the next hidden state is going to the same function. So this is like language modeling, because you are saying that you have so if you see the Desiderata, you see the Markov property. Any element can be predicted from its preceding elements using a fixed model. So the shared weights ensure that property, that every position is treated in a similar way. And if you look at an input xt, unlike a conventional neural network where all the inputs are in the first layer, here an input directly encounters the hidden state constructed from all the inputs that occur before it. The second point that the second figure that you see on the right, that is simply a shorthand notation for the time-layered network. So the reason we use this shorthand notation is because the number of time layers depends on the length of your input. So here, for example, you actually have a 5-sentence word. So I did not show the start and end tokens, but in reality, if you also show the start and end tokens, you're going to get 5 layers. For this particular sentence. So here I have shown only 4 of them for the first, second, third, and fourth word, and then you will have one as start as the input word and the other as end as the output word. So in this case, you can clearly see that if you change your sentence, so for example, if you had a sentence of 10 words, the number of input layers is also going to correspondingly increase. So in order to show that the fact that you have the same network with the same set of parameters which are being repeated, depending on the length of the input, you have this notation that you use, which is shown on the right. This loop, it should not be misinterpreted to think that you have a loop in the network. This is not really a loop in the network. You use this loop is simply a notational convenience which tells you that you should create a time-layered network in which the weights between the successive hidden states is, the weight matrix between successive hidden states is WHH. Now, in this particular case, I showed a case where in every time layer you have a single input and a single output. Now, this is not necessarily true for every application. Whether you have the outputs in particular are often very optional, sometimes even the inputs. So let's look at some variations of this type of time layering. So for example, we already saw the case, the very first case on the top left where you have no missing inputs or outputs. So language modeling is a classic example. You also use it for forecasting in time series. So for example, you're trying to predict the next value in the time series based on everything that you have seen so far. So that's very similar to language modeling, except that your inputs are real values rather than discrete values. Then the second might be, for example, image captioning, where your input might be the neural representation of an image. Now that neural representation might be constructed using some other neural network, such as a convolutional neural network, and that is fed into the very first layer. You don't feed it into later layers. And then it produces a variable set of outputs corresponding to the caption of the image. And the caption of an image can vary with the image at hand. And then the lower left, what you see is the example of sentiment analysis, where you have a sentence of variable length, so you have inputs, but you have missing outputs. So you only have a single class label at the very end. After you see the sentence, you will say, oh, this is a positive sentiment or a negative sentiment. And then you can have both. You can have missing inputs or you can have missing outputs. So for example, here you see language translation, machine translation. So the input might be a sentence in English and the output might be a sentence in Spanish. So these are all variations of the same basic architecture. Now for simplicity, I am just going to work with the one on the top left, where there are no missing inputs and outputs, because the recurrence equations are very simple, but the difference from these other variations is actually very straightforward, and we'll see examples of applications a little bit later. So, what are the basic computations that are performed? So, we already saw that you have this type of time layering of the recurrent neural network. So, here you have the two types of computers. One is the hidden to hidden. Now, each hidden state, what it takes as input is the values in its previous hidden state. It's a function of the values in its previous hidden state and its immediate input, the input in that particular timestamp. So at a particular time, all that a hidden state sees is the neural representation of the sentence, of the portion of the sentence that came before it. So now I'm always using the text example, because that's where recurrent neural networks are used most often. So every hidden state, all it will see is that segment of the sentence that came just before that point and the immediate word which is directly input to it. And it uses that with the weight matrices WHH and WXH to construct the next hidden state. And the way that's done is by multiplying WXH XT plus WHH HT minus 1 tan, and then applying the tan F function on it. Now, this is actually not very different from your traditional neural network, this type of computation. The main difference is that you're seeing the inputs at all the intermediate hidden layers. The inputs are not just in one layer at the very beginning. So this is really, recurrent neural networks are not very different from traditional feed-forward networks. Architecturally, they are actually quite similar. The main differences being in terms of the copying of the layers, the time layering, and the variable number of layers depending on the input. But otherwise, it's very similar. And then the output, YT, that's a vector of probabilities, can be constructed by multiplying the hidden layer at that timestamp with WHY. That's the weight matrix between the hidden and the output layer. Now, in this particular case, in this language modeling application, you would apply some, for example, a log loss function. And then sum it up over all the outputs in order to perform your full loss. So we'll see how that works a little bit later. Now, of course, again, this loss function and the number of outputs, it depends on the application at hand. So for example, if you had a sentiment analysis application, the output would only occur in the final layer. So now this type of architecture gives you flexibility for variable length inputs. So the reason for this is that if you look at the hidden state HT is defined in terms of its T input. So for example, if you look at H1 is a function of H0. H0 is often chosen to be a zero vector, the hidden state at the zeroth time step, and X1. So it's a function of H0 and X1, and then H2 is a function of the first hidden state and X2. So you can actually write H2 as a function of X1 and X2. In general, you can write HT as a function of X1 through X3. So you can see how the hidden state in each layer is a function of inputs of variable length depending on which layer that hidden state lies in. And that is the nice property of recurrent neural networks, because for sequences of any length, we can construct a fixed length representation, and that fixed length representation is inside the vector HT. And for many machine learning applications, having fixed length representation is very useful, because you can just treat it as a multidimensional data point. Now here I give an example of how a language modeling application would work. So here again I have that simple sentence, the cat chased the mouse. So so if you look at, for example, so here you have a lexicon of length 4. So I've just simplified it by using a lexicon of length 4, which is simply the cat chased mouse. So the occurs twice. So this is a sentence of 5 words with a lexicon of size 4. So if you look at the word the, it's a one-hot encoding. The input is a one-hot encoding with ones and zeros, which tells you that it's the word the. And then the output, so then the hidden layer produces some hidden states. We might not necessarily have any interpretation for the hidden states. So here we are just using 2 hidden states. So your matrix, your WXH, that matrix will have to multiply. So suppose you multiply WXH with XT, with X1. So if your X1 is a vector of length 4, your matrix WXH would have to be a matrix of length 2 cross 4 in order to produce a hidden state of length 2. And then you similarly multiply with the hidden state with WHY to produce the vector of probability. So it gives you a score for each word in the lexicon. So it gives you a score. So it predicts the next word. What is the, so here unfortunately it doesn't seem to give the best one. It gives mouse the highest score instead of cat. So it doesn't get it right because it gives mouse 1.7, it gives cat 1.3. Now note that in most cases you would apply a softmax on top of this, so it will actually give you probabilities with that sum to 1. Here I haven't bothered to use the softmax, so it's simply a score. And but if you look at the second word after you input cat, it's going to produce again a vector of probabilities, but here in this case it gives the highest probability to the third in the lexicon, which is 1.9. If you look at the third element in the output for chased, the second output, it's 1.9. So here it seems to be correct. So the loss function will generally, after applying the softmax, it will generally apply a log loss, and it will train on sequences in order to learn what these weight matrices should be, and that is standard for any neural network. Now, you can generalize this principle to multilayer neural networks. And multilayer neural networks, if you look at the recurrence equation, they are not very different from the single layer neural networks. The only difference is that if you look at a higher level layer, what it takes as input is one of its lower level layers instead of the one hot encoding of the input word. Otherwise, the recurrence equations are almost identical. The second difference is that the weights are shared across time layers, but they are not shared across the multiple layers between the input and the output. So here, for example, I have superscripted the weight matrix W with K, and this superscript K can vary from 1 through 3. So you will have different sets of weight matrices in each of these layers between the input and the output. So the first question arises is that how do you train a recurrent network? Now, training a recurrent network is not very different from traditional neural networks, because after all, a recurrent neural network is just a feed-forward network with a very special type of architecture where the inputs can occur in any layer, but that does not change backpropagation in any way. The only thing that you have to be careful of is that the parameters are shared between different layers. So what will you do? So for a given input, first you are going to run it through the network, and for that purpose, it's going to create as many layers as the length of that sequence. And then what you do is that you pretend that the weights are not shared. So let's say it's a sentence of length 8 and it created 8 layers. So you pretend that each of these 8 weight matrices is different. So for this particular input, you create you compute the gradients using traditional backpropagation with respect to each copy of the weights. So for each of those 8 copies, you will have some gradient. So you have these weights like WHH between hidden to hidden, input to hidden, or hidden to output. For each of the 8 copies, you will compute their gradients. And then all you'll do is that you'll add up the gradients over the various copies of the weights. And this is something that we already discussed in an earlier lecture, that's always how you handle shared weights. And then you perform the gradient descent update. And this algorithm is referred to as backpropagation through time. Now, one challenge with backpropagation with time is that the number of layers in the recurrent network, it depends on the length of the sequence. And in many applications, so for example, if you have a weblog application or a recommender system application, the number of layers can increase very significantly. So you could have thousands of elements in the sequence, and trying to do the forward and backward propagation, because it's going to create as many layers as the number of elements in that sequence, it's going to cause problems in memory speed and convergence. And the way in which you approach this is that you process the neural network chunk by chunk. So you use 100 around 100 sequence elements at a time, and you perform you can compute the forward states exactly using the final state of the previous chunk. So you have the state you have the value of the final state in the previous chunk. You use it to compute all the forward states in the current chunk. You compute the outputs in the current chunk, and then you compute the loss only over those portions of the output. So for example, if you had a time series prediction application or predicting the next word application, only the words that occur in that specific chunk, you are going to use the loss over them and sum them up, and you are going to perform the loss backpropagation over the weight parameters using only the current chunk. Now, this type of sampling, chunk-wise sampling, is very analogous to the stochastic gradient descent that is used in neural networks. Of course, training a neural network in general faces a lot of challenges because of the increased length of the sequence. And this is an issue that we will discuss in later lectures.